So let's go back to the one. So the last we left off, we had done this problem, if I can get it to show. So another way of showing polarity is by using partial charges, right? We know that the electron is going to be favoring, who's the electron favoring under this compound?
Oxygen.
Oxygen. So then we would give oxygen a partial negative charge because electrons are negative. And so that means that you're spending more time on the oxygen side than you are spending on the, let's say, the sulfur side, right? So then it's favoring one side towards the other. Or we could sit there and look at it just in terms of carbon. It's favoring this guy, and it's favoring this guy. But since we know the overall polarity is going to be going that way, so we'd want to draw it in that sense. That's one way, okay? So in the case of carbon trihydrogen chloride, in this case, the chloride is going to be favored because it's more electronegative than the carbon and the hydrogen. So the overall polarity is going to be going towards chloride, okay? So in this case, you could sit there and say, okay, plus, and then this guy is partially minus. Okay, so that would be another way of showing it, and that's the way of showing like the dipole moment by using those partial charges. Okay, so now knowing that, let's see, who do we have? Let's go. Taylor and Alberto. So can you guys do me a favor and draw the Lewis dot structure? So Taylor, can you do the Lewis dot structure for dihydrogen sulfide? And Alberto, can you do the Lewis dot structure for ammonia?
Okay.
Is it going to have a charge?
I think so.
Are you sure? Because if it did, wouldn't it say ion on the end of it?
Okay.
Yeah, the sulfide is kind of a loaded term. It can suggest that it's an ion, but it's also used to, when we do nomenclature, right? Particularly when it's covalently bonded things, we always use I to let us know that that's the end of that molecule.
Okay. So it's just H2S.
That's right.
Dr. Henry, did you say about Alberto do ammonia?
Yes.
He's not in the class.
Did he jump ship? He was there in the beginning.
He heard his name and he got scared.
Okay, so I was wondering, Alex, will you do it? Alexandria?
Yeah, ammonia.
Ammonia, yeah.
Okay.
So Mikey, since we have the dihydrogen sulfide completed, can you show us the partial positive and partial negative, and where would they be on the in the case of the dihydrogen sulfide?
Okay.
I have a quick question as they're doing this, Dr. Henry.
Yep.
So let's say you have, I think you did it on the previous slide, you have like sulfur in the middle, and then on the left you have oxygen, and on the right you have hydrogen.
Mhm.
So that would be considered a polar molecule, right?
It would be considered a polar molecule, yes.
Okay. It's not non-polar because hydrogen is weak compared to oxygen. So the strongest kid, I guess, takes everything for itself.
Yeah, exactly. Yep.
Okay, got it.
I don't know how to draw the partial positive, partial negative symbols. Is it
So
like
who's going to be partially negative?
sulfur?
Sulfur. So it's just a little, it looks like a funny D. So it's like this. And so then partial positive is going to be whom?
Both the hydrogen.
So it's the lowercase delta. That's what the symbol is.
Okay, yeah.
Okay, so what's this number thing I do? How do I do the number thing?
Oh, you want to do the formal charges?
Yeah.
Your formal charge would be, oh, you're trying to do what she's just keeping
Yeah.
track
What
of all
do I
the
have to do
electrons.
that?
What was that? She was keeping track of all the electrons.
Oh, okay.
And so that's, if you want to add that on there, then you can. Yeah. But okay, so now, Angela, what would be the formal charges for Leah? What would be the formal charges for ammonia? Struggling today.
Well, for nitrogen, you want the formal charges?
Not the formal charges, the partial charges.
Oh, the nitrogen will be partially charged negative, and then all the hydrogens will be positive.
Okay, piece of cake. Simple.
Mm-hmm.
Yeah.
Okay, so now if I put this guy in a magnetic field or electric field, electromagnetic field, and I have my negatives on one side and my positive on the other side, what's going to happen to my molecule?
Will it just be like suspended in between them?
Okay, and what else would happen? Would it just, let's say we had positives here, a positive plate here, and a negative plate over here. What's going to happen in this case?
Would they be attracted to the more positive side because they're partial negatives?
So who would be attracted to the, because you have both partial positives and partial negatives. So what's going to
Oh.
happen?
Would it dissolve the thing? Not
No.
dissolve it, but like pull it apart?
No, it wouldn't pull it apart. It would stay intact. So the charges are not strong enough to break those bonds.
Will it just rotate
It'll rotate.
like 90 degrees?
Exactly. So it's going to rotate and orient itself so that the negative is facing towards that positive charge, and then the positive is facing towards the negative charge. Okay, so we have a partially positive, partially negative molecule in solution. As soon as we turn on that electric field, the positive is going to face towards the negative is going to face towards the positive. And so you're just going to get orientation. So this is called polarizing a solution. So often we'll polarize a solution if we're trying to kind of control a reaction. So we want the reaction to take place on one side rather than the other. So we'll put this in an electric field or electromagnetic field to get the molecules to orient a certain way. And then we'll have like a place so that these guys can actually enter, or a solution that will come in and enter from one side, but then it would have access to, let's say, this point to attack on rather than the other side. Does that make sense?
Yeah.
Okay.
Have you done this before in a lab?
I did it in a lab when I was at UC Santa Barbara in one of my higher chemistry classes. It's a pain in the butt.
I was just about to say, it seems like it would be a pain in the butt.
Yeah, and then it sucks because you're trying to get, because it's all based upon percentage, you're trying to get a certain reaction to occur before another reaction. So you have this, in our case, we were using a pretty big molecule, and it orients, it gets a nice little orientation. And so you're going to be enriched in one compound compared to the other if you do it right. And so you're just doing these calculations. It's such a pain in the butt. It was a pain in the butt. But it kind of helps you in terms of industry and stuff. Understand what you can do, what's capable. Okay, let's move forward. Finally, chapter 8. Chapter 8 isn't too bad. Okay, so speaking of electric fields, so here, if we put a magnet on the side of, let's say, liquid nitrogen being poured into something. So liquid nitrogen or liquid oxygen. So if we put liquid nitrogen, nothing's going to happen. Liquid nitrogen is just going to flow right past the magnet with no effect at all. But liquid oxygen will actually suspend in the middle of the magnet, right? So kind of like what Mikey was kind of suggesting what would happen with that polar molecule. Now, the reason why this happens in the case of a magnet and in the case of oxygen is because oxygen is, you guys remember, I think we talked about this last time, paramagnetic and diamagnetic.
Yeah, you did go over that.
Okay, so what is the difference between paramagnetic and diamagnetic?
I don't remember which one is which, but I remember that one has all of its electrons like spread out across the shell.
Okay.
Oh, that's the diametric. The paramedic is where they don't. Or the paramedic is where they don't have the how do I describe it? Can I draw on it? I'll
Yep,
show you.
can. Yep.
All right. The first one is paramedic. The second one is diametric, right?
Yep. Yep. So the first one is paramagnetic, and then the second one is diamagnetic. Okay, because the second one is all paired up, right?
Or
So-
paramedic. Yeah.
Yeah. So that one is dio. So para means like for magnet, right? It's kind of a hint. Para for. So for a magnet. So this guy is going to be attracted to a magnet, where the diamagnetic one isn't. It's perfectly paired up. Okay, so basically that's what's happening in the case of the oxygen. So you have electrons that are not paired up. And so that's going to be kind of hard to see just by our Lewis dot structure, right? So if we have the nitrogen, we can't really see that. We don't understand it. So in this chapter, we're going to be talking about that. We're going to be talking about another way of looking at when we bring molecules together to sit there and determine whether they're going to be paramagnetic or diamagnetic, and then also whether they're going to want to form bonds together, right? Same thing in the case of the oxygen. You can't tell. Because if you look at this, it looks like everything's all paired up nicely, right?
Right.
Yeah.
So first off, we got to get some definitions to you, some new definitions. And we're going to introduce some new terms. Okay, so one of the first things that we're going to be talking about is valence bond theory. Okay, so in the case of the valence bond theory, we're basically saying that, and this is something that we already know, but we're going to just kind of emphasize it a little bit more, and we're going to give a little more clarity to it. So basically, for covalent bonds, we have the orbitals of the electrons, or the orbitals are basically going to be overlapping with each other so that the electrons can be shared. Okay, so there have to be two conditions met for this to take place. The very first condition is that orbitals of the atoms must overlap, and then the second condition is that each of those orbitals have to have at least one electron in them so that they can be shared. Okay, so that they can form that pair. Okay, so the other thing is that you guys look at between A and B. So if we overlap from N to N, we get more contact compared to if we go from, like, let's say one is in the x-axis and one is in the z-axis. And so you're just getting this partial amount of overlap. So you're not getting a lot of overlap between the two here compared to the overlap here for when you have things end to end. Do you guys see that?
Yeah.
Okay, so that's going to be kind of important because we need to pay attention to how things are going to be oriented. So that's why we made reference earlier when we talked about the PZ, the PY, and the PX, right? So to kind of let us know where they're located in their orientation, okay? And we'll talk more and more about that. Okay, so again, going back to what we've been saying since the very beginning of chemistry, at the end of the day, it all deals with energy. So in the case of hydrogen, the reason why hydrogen forms a diatomic molecule rather than just having single atoms of hydrogen is because energy, right? So this is basically an energy diagram of hydrogen. And so this is hydrogen when it's a diatomic molecule. And then as we start moving the hydrogens away from each other, we shoot up in energy, right? And this guy becomes, even though they're close, they're still high in energy relative to our diatomic. And then if we move them completely apart where there's no interaction at all, that's even higher in energy, okay? So hydrogen prefers to be a diatomic because it is lower in energy compared to the individual atom of hydrogen by itself. You guys get that? And so in nature, we find hydrogen in this form because it's much lower in energy than the hydrogen atom alone. Are you with me?
Yes.
Okay.
Mhm.
So at the end of the day, the reason why a lot of atoms will form compounds, covalent compounds, or even ionic compounds is to try to get to a lower energy level. So that's going to be very, very important. It's important that you guys understand that because that's going to kind of dictate what those atoms are going to be willing to do to get to that lower energy state, okay? So we've talked about overlapping orbitals. So in this case, we have two p orbitals that are overlapping end to end. And again, that's going to give you the greatest amount of overlap, where B gives you much less overlap, okay? And so that's going to play, again, another part of it. So we want to make sure that we're getting the maximum amount of overlap because that helps with stability. It helps keeps that compound or that molecule intact, okay? Okay, so I'm going to introduce a new term called a sigma bond. A sigma bond is when you have overlapping occurring in one spot. So here, these are two s orbitals, because we know that the s orbital looks like this, the s orbital looks like this. These guys are two s orbitals that are overlapping with each other. So this is called a sigma bond. This guy is an s orbital, and this guy is a p orbital. You guys remember what p's look like? And we have an s and a p overlapping. This is also a sigma bond. And this guy is two p's overlapping end to end. So a p and a p. Also called a sigma bond. Okay. Now the thing about a sigma bond, the sigma bond is only represents a single bond, right? So when we're talking about, let's say, oops. This is an example. This bond here is actually a sigma bond, right? That single bond, that overlap between those two. In this case, it would be 1s and 1s. So it would be an example of this guy overlapping. That's an example of a sigma bond. Are you with me? Yes, no, maybe?
Any combination of s and p orbitals is a sigma bond?
Yes, long as they have the maximum part of overlap. Yes.
Okay.
Okay. So yeah, it could be it could be the px, it could be the pz, or it could be the py, long as you're maximizing the overlap. Okay. Okay, so this here is called a pi bond when you have side by side and you have two regions of overlap. Okay, so these guys represents multiple bonds. So this guy would be like a double bond. Okay, so a single bond is always going to be just sigma bonds. A double bond is going to be a pi bond and a sigma bond. And then a triple bond is going to be a sigma bond and 2 pi bonds. Okay, are you with me? Okay.
Kind of.
So pi, because it's 2-pronged, pi day, right? So 2 pi, or sorry, pi is 2-pronged, so think about 2 regions of overlap.
Oh, okay.
Do you see it?
Or yeah.
Okay. Okay, so now let's see if you guys paid attention to what I was saying. Maybe. Okay. So what type of bond is going to be hydrogen chloride?
Sigma.
Okay, so you're right. It's going to be a sigma bond, no pi bond. What about oxygen gas?
It's both 1 sigma, 1 pi.
Okay. And then what about nitrogen?
1 sigma and 2 pi.
Okay, piece of cake.
Yeah.
Okay, so here, can you tell me how many sigma bonds I have and how many pi bonds for this compound?
Are there 7 sigma bonds?
So let's count. We have 1, we have 2, we have 3, we have 4, we have 5, we have 6, we have 7. And then remember, one of these guys are going to represent a sigma bond, and the other one is going to represent a pi bond. And so that's 8, and that's 9. We have 9 sigma, and then how many pi's?
2.
The other one represents a pi, so 2 pi's. So does it make sense?
Kind of.
Kind of.
So
Okay.
if it was 3 bonds, then it would be
If it was a triple bond, so you're saying if
Yeah.
it was like this, okay, so this guy would be how many sigma and how many pi?
be 8 sigma.
Okay, whoops, let me finish writing these out. It's being lazy. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9.
I can't count.
Okay, and then how many pi bonds?
2 of them.
1, 2. Okay, does that make sense?
Yeah.
Yeah. So 9 and 2. Yes, good job. Okay. Oops. Okay, so identify the illustration that depicts a pi or sigma, a sigma or pi bond. Okay, so, and first we kind of have to draw it out. So we have a side-by-side 4p, 2p orbital overlapping. So what is going to be the difference between the 4p and the 2p?
The 4p is bigger.
4p is going to be bigger. So we're going to have something like this. So here's our 4p. And then this guy is our 2p. Okay. Okay. Is this pi or is this sigma? I heard somebody say it under their breath. It's pi. That is correct. Okay, what about end-to-end overlapping of 4p, 4p? What is that going to look like?
They're both like the same size and everything.
Okay,
But they connect on one end.
but they connect on one end. That's right. Okay, so those are the same size. Okay, so
that's sigma.
that is a sigma. That is right. Okay, what about end-to-end overlapping 4p and a 2p?
Would it be a figure 8 and a circle? Oh wait, no, never mind.
So what is it going to be? So if we have one figure 8, what is the other one going to look like?
It's another figure 8.
Be
Just
another
small.
figure 8, but smaller. That's right. Okay. Oops.
So still.
Okay,
it's
so
still
then
sigma?
that is still a sigma. That's right. Good job. Piece of cake so far?
Yeah.
Okay, now we're going to make it a little bit harder. Okay, so this is kind of setting us up for understanding. So we have pi bonds and we have sigma bonds. Okay. Now I'm going to talk about hybrid orbitals. Okay, so hybrid orbitals, let's see, best way of saying it is that the hybrid orbital is basically going to be combining an S and a P, or an S, P, and a D, or all of these orbitals together to make what we call a new orbital, which we call a hybrid. So, and I'll kind of give you an example of it, because until you see it, it's going to be a little bit hazy. So, but there are a couple of things that we want to keep in mind, some of the rules, okay? And that's what it's going to be giving you here. So, hybrid orbitals only exist in covalently bonded atoms, or so covalently bonded compounds. They're not going to exist in the atom alone. So they only exist when things are getting ready to covalently bond. Okay. Hybrid orbitals, they have a shape and orientation that is going to be different than the atomic orbitals, right? So they're no longer going to look like, you know, how the S looks like a perfect circle, it's a sphere, right? And then the P looks like dumbbells, right? Or figure 8, right? So they're no longer going to look like that. They're going to be their own shape. And then we'll kind of show you what that's going to look like. So the set of hybrid orbitals that are going to be generated by combining orbitals together. So it's going to be combining like an S and a P to make the sp orbital, right? Or the sp2. That's meaning it's going to use 2 of those p orbitals. Okay. And so, and then at the end of the day, you're going to end up with, if you use 2 orbitals, then you're going to end up with 2 sp orbitals. Does that make sense? So if you use an S and a p orbital, then you're going to make an sp orbital. And I'll show you that too. It'll make a little more sense. And then lastly, all of the orbitals that are made by the hybrids are equivalent to each other. So they're going to have the same shape towards each other, the hybrids will. And then And it's going to be dependent on the Vesper theory. It's going to be dependent on the electron pair geometry. You guys remember electron pair geometry? If it has 4 attachments, it's what?
It's a tetrahedral.
Tetrahedral, right? If it has 5 attachments, it's what?
I forget the name. It's really long. Is it like
Trigonal
bipyramidal?
bipyramid.
Yeah.
Yeah, trigonal bipyramidal. Yep. Okay, and if it has 6 attachments, it's what?
Octahedral.
Octahedral.
Octahedral. Okay, and then the last rule is hybrid orbitals are going to overlap to form sigma bonds. So you'll never form pi bonds with hybrid orbitals. So only unhybridized orbitals will overlap to form pi bonds. Okay. Okay. So this is just kind of giving us an idea. Okay. So here, water has basically 4 regions of electron density. So we have 2. So this represents oxygen. So we have the 2 lone pair, and then we have the ones that are going to be overlapping with hydrogen, right? And so here, B basically showing you the overlap between the hydrogen and each of the hydrogens right there. And you notice this guy kind of represents a hybrid orbital being shown because these guys are all 4 the same. And then, but these 2 are going to be the ones that are going to be forming bonds with each of the hydrogens. And as a result of that, it changes the shape of the natural shape of the orbitals itself, because normally this would be a 109 angle, but when we put hydrogen on here, now we have a 104.5 because of that hybrid structure. Okay, so let's talk about the sp hybridization. So here we have beryllium. So you guys can see at the very bottom, beryllium has how many valence electrons?
2.
It has 2 valence electrons, right? And both of those are going to be in the 2s, right? In terms of, and it's going to be in 2s, and none of them are going to be in a 2p or anything like that. So when beryllium is alone by itself, this is the way it's going to look. But when it hybridizes, when it gets ready to form a covalent bond, what it does, it takes this orbital and it takes one of these p orbitals and it mixes it together. So here's that s and here's that p. It mixes it together to make what is called the sp orbital. So these are 2 sp orbitals. Okay, so the sp orbital are lower in energy than the 2s, than the 2p orbitals, but they're higher in energy than the s. So the hybridization causes them to be lower in energy overall than the 2p, but higher than that 2s. And so it prefers that rather than, because in the case if beryllium was just to use the p orbitals, it would be higher in energy compared to using that sp orbital. Does that make sense? So in other words, the 2p here, these are unhybridized. They are higher in energy than those sp orbitals. Okay, so in this case, what was that?
Does it like move it into the hybridization state just because it's easier to bond that way? Is that the purpose?
Yes, it does it just because it's easier to bond that way. It lowers the energy of the 2p by making it a hybrid, and it makes it more attractive for bonding because it's lower in energy. Does that make sense?
Yeah.
Okay. So now this guy is capable of bonding with the chlorines in this case. Okay, so then you'll have chlorines, which would be in our, it would be in our 3p. So we take that 3p would overlap with this. So this would be the 3p of chlorine overlapping with both of these sp hybrids. Okay. And what type of bond is this again? Between the chlorine and this is the beryllium.
Is a sigma bond?
That's right. This guy would be a sigma bond. Yeah. Okay. So does that make sense about the hybrid? Yeah, no, maybe.
I'm a little confused.
Okay, so let me see if I can get it explained a little bit better with the next one. Right. So this guy is called the sp hybridization.
Mm-hmm.
Okay. So this guy is called the sp2 hybridization. So in this case, let's say we're using a molecule like boron. Boron has how many valence electrons?
3.
So 1, 2, 3. So we have 2 in the S, 1 in the P. Now, this is what it looks like when it's just boron. Okay. Now, when it gets ready to bond with, let's say, hydrogen, what it's going to do is hybridize itself. So it's going to take this guy, it's going to take this guy, and it's going to take this guy. So we have, that's where that 2p comes from. So it takes like either the X or the Y, and it's going to combine these all together. So we take all 3 of these. So here's the X and the Y. So the X and the Y, PY, and then we take that S, okay? It combines them all together and like puts it in the blender, and then it gets out. This would be sp2. This guy would be sp2. And this guy would be sp2. Okay, so the sp2 represents the hybrid that is formed. So the sp2s are lower in energy than the 2p by itself, but they're higher in energy than it would be just that 2s. Okay, and so now these guys are ready to bond. So then they're able to bond with each of those hydrogens. So these hydrogens would come in and share their electron with these guys. So now we have a hydrogen here, a hydrogen here, and a hydrogen here. Is that a little bit clearer? Is it making a little more sense?
This is called just what, hybridization?
Hybridization, that's right.
So if I was to like look at videos on YouTube, that's what I'd put. Hybridization.
Exactly. Yep.
Okay.
Yep. Okay.
In the second shapes, like with the sp2.
Yep.
The small end, is that general shape or is that
So
just
remember, you're mixing these guys all together, so they're kind of forming a new shape. So what it does, it makes another shape that looks like a little baseball bat, right? So one is really small, one side of it is really small, and one side of it is really big, right? Or like balloons with the nipple. Right? See my balloons with the nipple, right? So in that case, these are like 3 balloons with the nipple that are coming together for bonding, right? So it mixes those guys up so that they form 3 independent new shaped orbitals that we can use for bonding. So it doesn't look like, if you look at it, it doesn't look like the P and it doesn't look like the S. It looks like its own shape. It has a little nipple on one side and a big one on the other.
Did you get those balloons just for that analogy?
Yes. No, I had them for something else. Yeah. Okay, does that make sense?
shapes make sense?
You said the shapes make sense?
Yes.
So what you're doing is you're merging all of these guys together, right? You're bringing them all together and you're like, okay, I'm going to mix this all together and I'm going to make 3 equal new orbitals that are going to be lower in energy, right? So I'm adding all of these together and then I get, that's my first one, this is the second one, and this is the third one. So this represents that first one, this represents the second one, this represents the third one. And then they're all at the same energy level, so then they all can hold an electron. So you guys notice that as well, that we have 3 electrons, and we have 1 electron in each one of those. So then those can pair up and share electrons with the other. So this is one of those hydrogens that are here in peak going in the other direction. This is that other hydrogen that's going to pair up here. And this is that last hydrogen, the electron from that last hydrogen that's going to pair up there. Okay, so we're just trying to make it, we're trying to make ourselves more attractive for somebody to come and pair up with us, right? Because nobody wants to be with somebody who's high maintenance or high energy, right? You want to be with somebody who's lower in energy, you know, that is accommodating for you, right? Was that true, or am I making stuff up here?
Makes sense. Okay, so why are we using 2 of the P? Okay, so back to the orbitals and isolated B atom. Why are we taking 2 of those when there's only 1 of them in the 2p orbital?
Why are we taking 2 of what?
Of like the electron, not shells, but like,
Because we're taking the total altogether is 3 orbitals altogether. There's 1, 2, 3, because there's how many valence electrons to work with?
3.
3, that's right. And so we don't want these guys to be paired up with ourselves. We want these to be paired up with someone else, right? So we're going to be sharing one of them and somebody else is going to be providing the other one, right? So we need 3 orbitals to account for those 3 valence electrons that we're going to be used for reacting, right? Because boron has 3 valence electrons that it can use for reacting. Beryllium had how many valence electrons?
2.
2. So then we made sp, those only 2 orbitals, right? So go back.
Okay.
So after they bond, do the orbitals go back to like the regular ones?
No, they stay, because remember, they're there because it's lower in energy, because otherwise they would have to go up to that 2p. Well, the sp is lower in energy than that 2p, right?
Right.
And
So the
so
hybrid shell just gets like filled with the other one that it's sharing.
that's right. Yeah.
Okay.
Yeah. And that's, again, lower in energy, so it's happy. Okay. So if we have something like carbon, well, let's move forward. We'll come back to this. So if we have something like carbon, carbon has how many valence electrons?
4.
It has 4. So we would have, this is what carbon would look like. It would be 2s by itself. And then it'd have 1 here in the 2 p's. So that's 2p. So when it hybridizes, what is it going to do? How many hybrid orbitals will it make?
Would it be like sp3?
Okay, so it'll be sp3. And how many of those will we have? How many?
4.
4. Okay. Okay, so now this guy is ready for bonding. So if we had 3 or 4 H's, then we'd come in, the H's would come in and provide theirs. And then we get this. Okay.
I just have one more question. Is this like a unique case of covalent bonding, or is all covalent bonding done like this?
Some of covalent bonding is done like this, right? So it's a large portion of covalent bonding is done like this, because you'll actually start you will actually start making other type of hybrids, right? So when we start talking about sulfur and phosphorus, right, those guys will make special hybrids. So they'll actually start incorporating the d orbital, right? So a lot of times we're going to be doing this. And then we're going to get into something else a little bit later called bonding and anti-bonding. Okay.
Okay.
And then that'll kind of explain, okay, will it really happen or will it not happen? Okay. Okay, so let's go ahead and stop here, and then we'll pick this back up on Monday. So I'll meet you guys in lab, and how long do you guys need to get your stuff?
15 minutes.
Okay, so you want to say 7:30?
Yeah.
Okay. So I'll meet you guys in lab at 7:30. So that gives me time to go to the bathroom, make a cup of coffee, have a beer.
All right. Bye.
It'll be a party.